miss that one, that they cannot, they can easily catch it up. Okay, let's see that number 2. Number 2, see, meaning Hospital Incorporation instituted an electronic medical record system in January 2014. You want to know if there has been a decrease in reported medical errors. Your data look like this. See, these are hospitals. There are more hospitals. Okay, go around. Okay. The experimental units are hospital. This is before, this is after. See, a lot more data. Which of the following would then be acceptable method of answering the research question? Is there a significant decrease in error from the prior year? See? So that means that we're going to set this up. See, Y1, reported medical errors in 2013. If you want, you can say Y1. Y1 is given that as a, like errors underscore 2013. Y2 reported the medical errors in 2014. This is the different form. You can give like a Y1 or this way, experimental unit hospital. Then you get the difference between those two, before and after, or that Y1 minus Y2 or Y2 minus Y1, doesn't matter. Then the pair dependent test. See, the pair dependent test. What is it that your test would be? Your test would be, I forget to put the test. Okay, test would be, I'm going to put the test. Oh, I'm sorry, it's already there, I think. No, it's not there. H naught equals D versus HA D not equals 0. See, D H naught is that there's a difference. There's no difference between the errors. Say it would be have the same errors versus HA D not equals 0. Then for that one, part is part C and D. What is part C and D? Oh, I'm sorry. Oh, A. Oh, C and D. That's what I'm telling. C and D. In C, if the C means the pair dependent test, you can utilize this pair dependent t-test. If that's the case, your test statistics would be this one, which is distributed according to t distribution with the degrees of n-1, number of hospital -1, or you're going to square both sides. You cannot square. Then this one square, when you square, you're going to put that d square on either side of that SD squared -1. In that way, that similar, that formula can be derived for the multivariate case. If that's the case, now instead of working with t, you can work with F distribution. Instead of that one, if you are using F distribution, repeated measures and over, there's another way to get this done. The answer should be, for a situation like this, either you can use the pair t-test, dependent t-test, or repeated measures. Under the repeated measures, you can tackle that one in 3 ways. Univariate completely randomized design. Univariate complement randomized design, sum of squared total equal to sum of squared between. B stand for between, sum of squared within. And then you build up F like this, mean squared B divided by the mean squared within, which is distributed according to F G minus 1. G minus 1 is the number of groups. How many groups we have? We have 2 groups. See, n minus 1 is total number of observation minus the number of groups. See, that's the form. Or the same thing you can tackle like a univariate randomized block design. This is a CRD design. See, this one RBD design. See, CRD. I'm going to write this one CRD. CRD means completely randomized design. Or block design, randomized block design, RBD design. See, RBD design. See, univariate, but univariate randomized block design. Or you call that one univariate repeated measures ANOVA model. If that's the case, sum of squared total equal to sum of squared between plus sum of squared within plus sum of squared residual. Here residual is nothing but within. See, same thing. Within and residual would be the same, but here not the case. You can remember how we built up the residual. You had this another one. There's another one over here, sum of squared block. Can you remember? Sum of squared block. So if you subtract, with that sum squared, within that sum squared block, you get this one. Can you remember? So this one, then F should be mean squared. This one treatment. This is called the treatment all the time. All the time this treatment. MS residual, which is G minus 1. See, G minus 1, N minus 1, G minus 1. G means number of groups, N means number of individuals, subjects, or hospital in this case, or multivariate case. In the multivariate case, you use the F, which is this one divided by this much, N minus G, N minus 1 times G minus 1. See, M, see, vector, this one. These are V. If you want, you can do by hand. You can do when you run the SAS. That printout will produce pretty much everything. G minus 1, N minus G1 plus 1. See? In this case. So that's number 2. So number 2 answer should be they ask that for this kind of a scenario, you can tackle pair dependent t-test or repeated measures. See, we conducted an experiment of the effect of a computer-assisted instruction on student grades. Students were tested at the beginning of the semester and again at the end of the semester. The experimental groups scored higher. Partial output from the repeated measures analyzed given below. See, partial one. See, look at what. This is partial one. Even though this is a partial one, what is a full one? We have to have a clear idea what's going on over here. It's not simply that give the answer. We can give the answer once you have a clear idea on this one. Look at. So see, it's kind of like a one between and one within factor or categorical variable design. See, one between and one within. What is the one between? Between means between the experimental group and the control group. Experimental group, I'm going to say E, control group C. We don't have this setup, but by looking at that output, you can come back and have a look at it, what kind of a design they have already adapted in the very beginning in order to produce that kind of a result. Then your Y would be your grade, time within variable or repeated measures variable or factor variable. Since we have a categorical, we're going to say factor. This one also, if you want, you can say factor. It's sometimes we're going to call the class variable, group variable, between variable, or between factor. It has a classes. See, 2 classes on this one. See, but this is one. This is one between. This is another one. See, what is my variable? Variable is nothing but school. They say the school for that one. This is time. So the beginning of the time, beginning of the semester, I'm going to look at my grade. I'm going to label that one as a grade 1 or grade before. This one grade 2, end of the semester, like that. This is a formula that will govern this kind of a scenario. See, in a situation like this, in a repeated measures equation, yij mu plus rho I plus alpha I plus beta k plus alpha beta jk. What those mean? So this one, rho I means individual effect, subject. This is the effect coming from individual. This is the effect coming from due to the factor 1. Factor 1 is what? Time. This is due to the factor 2, which is school. This is AB, interaction. See, that's the interaction between factor 1 and factor 2, which means time times school. That's how you have that time times school in that output. See? Time times output, and then epsilon ijk is the error term. So I gonna go from 1 to n. I means that number of individuals. See, I think it's not right. I'm sorry, ijk. This one j, this one k, and jk has the alpha and beta jk. Okay, so then that's the interaction term. See, then I'm gonna go from 1 to n, number of hospital. See, number of groups. Ij gonna go from 1 to a. I call that one a instead of g now. A equals 2. we have only two options. See, two options. Sorry, time, two options, and K, two groups. As well. So actually, this is the way that how they built up. We don't have to worry about this formula. I'm just showing you for the sake of just showing you. That's how they got that one. Their corresponding degrees of freedom. Sum of squared for the subject, sum of squared of factor 1, sum of squared of factor 2, sum of squared of the factor 1 times factor 2, sum of squared residual, sum of squared total. We have 1, 2, 3, 4, 5, 6. But on our output, they don't show in all of them. They show only the 2. See? Time and school. Time means like a factor. Factor A, factor 1. It's a factor 1 times factor 2. See? That's all. They're going to show that one, those two only. And degrees of freedom for the subjects in -1, degrees of freedom for factor A -1, this one B -1, this one A -1, B -1, this one N -1 times AB -1, this one ABN and -1. So out of this one, this is the thing. It should have been like this way, but they have given only the numbers, that the places, this entries and this entry only. See, it's supposed to have like all these entries, but we don't need that one. But I'm just showing to that, make that our discussion complete, and that you have a clear idea what's going on. So this in my, we don't have that one. We have a factor which is time. We can see 1. That's how we get 1. See, on the output you can see 1 here, 1 and 1. See, time times school also time, interaction term. See, because 2 minus 1 is 1. Then there are entries being already given. This entry and this entry. The rest are not given, but it's okay. And for A and B, equivalently, the simultaneously you can answer both. Okay. So let's look at that, what they were asking about. Do this data provide evidence for the effectiveness of the experimental treatment? Yeah, this is the treatment. See, it's a treatment. See? It's a treatment. So that if we go back to this one, I'm gonna say the difference. See? Difference of, see, in control group, difference of what? Difference of the grades before and after in control group. The same as in the experimental group. See the difference. I go to the difference versus, oh, this is not equal. Not equal. See, or equivalent, you can say it's not, treatment is not effective. And the HA, you can say treatment is effective. In order to test this one, you're going to look into the p-value related to that one. No? Simply. See? Since p-value for the factor 1 or within factor or repeated measures factor, which is time, is 0.007, 0.007, see, which is less than 0.05, we reject H naught at the 0.05 level and infer that the treatment is effective. Okay, that's how A and B both we can answer at the same time. Okay. Same time. Okay, let's go to the next one, number 4. Number 4. Hypothesized. I hypothesized that a sedentary lifestyle had a negative effect on a physical and mental health. I conducted a maneuver with the sedentary, yes or no, as my independent variable and 2 dependent variable, BMI mental stress. See, mental stress index, BMI body mass index, this one mental stress index. MSI and BMI. Multivariate tests are shown below. See, what is the hypothesis? Like they were given this one. So let's build this up. See, so we have a, see, our factor is what? Categorical. What is the factor name? Sedentary. It has a yes or no, but it's going to take care. But when it comes to the response, Y variable has a two variable. We're going to tackle 2. two variable at the same time. P equals 2. See, two variable. One is mental stress index, MSI. The other one is body mass index, BMI. That the mean model, if you write the mean model, the aid of Yij vector, okay, for the vector. Mu I, excuse me, mu I means like I'm gonna say I goes from 1 to 2, two groups, either yes or no group. But the J gonna be number of elements in this one. They supposed to have like a different numbers or same number, doesn't matter. Okay. So if the different numbers, we put the Ni here, same number, we put the N for both groups. Okay. And the effects model, I'm gonna put the effects. That's a, with the aid of this one, with the aid of that group mean. This one overall mean plus the effect plus the error. That's this is the model. This is the model. See? This is the model. Now we have to see what. Now we have to see. Let's say that you want to check something like this. See? Whether yes group equivalent to the no group versus see, not T. So what are you going to use? You are using T squared. See, you are using this one. This one is connected with the F like this. You know that one. It's like a multivariate approach for the repeated measures. Multivariate actually, see, multivariate approach. Simply say multivariate. Multivariate T squared. See, in multivariate case, we have T squared divided by N1 plus N2. N1 plus 2 means N plus N2, okay? Because they both have like the same sample sizes, you can see like this. And this F can also be derived as follows. See, you can get the treatment like this. See, you can remember that with the vectors, it's called the total. Total is nothing plus the B plus W or H plus C. And sum of squared treatment, that's called the B or H. Sum of squared residual, called the W or E. And the degrees of freedom for this guy is summation of Ni. I goes from 1 to G. G is the two groups here. G equals 2. And the treatment G minus 1, this is there. See? All these degrees of freedom. When you have something like that, you can straight go to the Wilks lambda. In multivariate case, we are using the Wilks lambda. That's how the Wilks lambda come into the picture. See? Wilks lambda is nothing but see, W over total, W over B plus W, and their determinant. That means their magnitude, see, of this these matrices. See, this one. Absolute value. Okay. Absolute value. The determinant. So part A, this equals to that. That means see, mu of MSI, mental stress index, and mu BMI, both see equals to that. See the other group, MSI in this group and MSI in that group. See, so if I write this one very clearly, MSI in ES group, MSI in BMI in ES group, MSI in no group, no group, and ES group, no group, no group, like that. I added this one. See, ES group MSI, ES group BMI, same as that one in the. See, when you get that several variables, you can even see the equivalence among those two. So when you go to that univariate, no, here look like a multivariate. See, even the two groups, still you can use them. No, see, BMI Y, BMI no, then they are not the same. Since p value for the Wilks lambda less than 0.01, which is less than the 0.4, we reject H naught at the B value. And the sedentary has a relationship with the BMI and SMI. Sedentary affect BMI as well as SMI. No, sedentary gonna affect to the so that body mass index as well as to the what is the other one? Oh, not the SMI. It should be MSI. 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 Mental stress index. Sedentary affect to this one. See, that's by looking at the Wilks lambda. Wilks lambda, Pillai trace, or Hotlin lowly trace, or rho is greatest root. See, we all have this one. See, would they have a number of degrees of freedom? Degrees of freedom. See, denominator degrees of freedom. This one. And remember that we might know this one. What is that? This one. Degrees of freedom of numerator. Numerator degrees of freedom is P. P equals how many variables? 2. What are the variables? BMI and SMI. Would that be 2? Yes. Then how about that the other one? The other one is summation of all the total number of observation minus P minus 1. P is 2 minus 1. Then 3 has been taken out. So let's add to this one 3 and see how many. So 47,331. 47,331 entries. This is 47,331 minus 2 for P. See, 2, that's a total. See, that's a total. It's a total. That's the same thing that sometimes this one earlier I wrote with the sum of that. Anyhow, that is a total. See? And you subtract 2 and subtract 1. Okay. So then they have a relationship. So let's go to the next one. Four multivariate tests are shown above. All have the identical F value and probability. If you do not get identical results for all our multivariate tests, there's an error in your code in no data. Is that true or false? Let's see what they were talking about. Let's build up that discussion. See, the multivariate test number 5. We have a Wilks lambda, which is that within matrix divided by the total matrix. Absolute value, say absolute value. Hotlin lowly, trace of this guy. See, Pillai trace, this one. See, rho is greatest root. It's the largest eigenvalue of this guy. Okay, these are the factors that we have taken into account. These all have approximately F distribution under the null hypothesis. It's all have a F distribution, F distribution, F distribution, F distribution under H node. With large sample, these four test statistics are nearly equal and will give essentially the equivalent conclusion. Okay? With large sample, these 4 test statistics are nearly equal. When you're using like a huge massive sample, they were all the same, pretty much the same. See? They're all the same. On the other hand, with 2 groups, these 4 statistics are equivalent and equal to the F value. With 2 groups, these 4 statistics are equal and equivalent to the F value in Hotlin t-test. When they have a 2 groups, with 2 groups, these 4 statistics are equal and equivalent to the F value in Hotlin t-test. 4 moderate sample, 4, sorry, this one 4 moderate sample sizes. The Wilks, Hotlin lambda, and Pillai methods have similar values. Similar power. Okay, similar power. Roy's method appear to be the best only when there's a difference in just one component of the mean vector and only one of the group is different from the other. Pillai trace may be the most robust to non-normality, but transforming the data is suggested if the model residual shows departures from normality. So this shows very good robust, may have been robust to non-normality. Most cases it's non-normality. All the cases we can assume that our data are normally distributed. You have to remember Yij, I wrote that Yij all the time. My data are normally distributed. It's an assumption. But in practical application, that's not the case all the time. If it's non-normally, you have to go to different. So because of that reason, see, yes, for two groups, these four statistics are equal and equivalent to the Hotlin F. Since we are using two groups, see, two groups, we can make a conclusion based on that all the facts. Since we are making two groups, see, yes or no, two groups. The comparison is done between two groups for two variable, these two variable. Okay, so because of that, yes, see, really, if you do not get the identical results, you have to get the identical results for all four multivariate tests. See, all these related to the thing, lowly, there is an error in your coding no data. Yes. Okay. So I will tell you over here. Now I'm gonna just upload this everything for you guys to that have a look at it later on. So if you miss anything, okay. So look at it. I have a conducted MANOVA to compare the average length of stay loss and daily cost of care cost among four groups. Now this time you have a four groups based on payer. The status of his that payers insurance, medical, Medicare, private insurance, and uninsured. My hypothesis is that the uninsured group differs significantly from the others. How would you code this contrast? See, my hypothesis is that uninsured group, I'm going to keep the uninsured group fixed and see whether how I'm differ from the others. I'm not looking into the difference between two consecutive that groups, but I'm going to keep this one with respect to this one uninsured group, how the other groups like a medical, Medicare, and private insurance groups gonna differ. If that's the case, how could I'm gonna write the this is a multivariate. Remember, how do I write the contrast? Okay, let's have a look at it. Okay, see, this is the scenario. See? So the Y1 is the average length of stay, allows. Y2, daily cost of care, cost. So you have four groups. See, factor is what? Payers, insurance status. See, you can say you can go by the name Medical, which is numbered by 1, Medicare 2, private insurance 3, uninsured 4. See, but you are talking about in Y variable, we have a 2, loss and cost that will Y vector will take care of that. So I'm interested in mu1 vector, okay? Mu1 vector minus mu2 equals 0. There's no difference. Mu1, see, are they different? Uninsured group differ significantly or not. See, my hypothesis that the uninsured group differs significantly from the others, from the others. See? So this one minus this one. See? Not 1 minus 2 and 2 minus 3, the way that we tackle that one when you have like a repeated measures. Can you remember? In order to tackle that one with the aid of that multivariate analysis, what we did was that mu1 equals mu2 equals mu3 equals 0, pretty much all are zeros. Then you break down that one to mu1 minus mu2 equals 0, mu2 minus mu3 equals 0, mu3 minus mu4 equals. That's not the case over here. I'm keeping this one fixed, mu1. If that's the case, how could you gonna write this the code? So before that one, if you have a something like this, how could you gonna just, let's say that we can have a look at it, one of them, this one, this difference. Okay, this difference, how could I'm gonna write with the aid of the contrast? Okay. See, I'm just simply writing first one, mu1 minus mu2 equals to 0 vectors versus HA mu1 minus mu2 not equal 0. Sorry, not equal 0. See? So I'm gonna call this one my psi. See, psi is the combination of what? Contrast. The contrast means I'm gonna put Ci mu I, this contrast, this one. I'm trying to write with the aid of the contrast in this format. So I'm going to say I, Ci is like a scalar, this is a vector. I goes from 1 to 2 because I have only 2 groups. So I'm going to say C1 mu1 plus C2 mu2 mu1 minus mu2. But I have a 4 groups. When you have a 4 groups, the rest are zeros. See, rest are zeros. See, rest are zeros. Okay, I'm gonna make it clear over here like this. C2 plus. Okay, I'm gonna write mu3 plus 0 mu4 mu1 plus 0 plus 0. Okay, for you to see. So I did some kind of a change. See, this one, but I'm telling you C1 mu1 plus C2 mu2 plus 0 mu3 plus 0 mu4. That means mu1 minus mu2 0 0. C1 is 1, C2 is negative 1. Sorry. C2, sorry. C3 equals 0, C4 equals 0, even the G equals 4. Sorry, this one should be 4 because we are using contrast. Okay, we are using contrast. C1, C2, C3, C4 equals 1, negative 1 plus 0 plus 0, which is 0. Okay. So, okay. See, this should be not 2, it should be 4. 4 because we have 4 groups now. So we go to the original one. Even though I compare that one, they should be even taken into account because of this we're gonna write in this format. We are trying this one in as a contrast. For C1 mu1 plus C2 mu2 plus yeah, okay, yeah. C1 mu1 plus C2 mu2 plus 0 mu3 plus 0 mu4, which is same as mu1 minus mu2. Okay, I need this one. That's what I need. Plus, I'm talking about my left hand side, this part. Okay, I'm building up this part. I'm building up this part. Okay, I'm building up that part. Okay, so that one C1 mu1 plus C2 mu2 plus 0 mu3 mu4, which is mu1 minus mu2 0 0, where C1 equals 1, C2 equals negative 1, C3 equals 0, this one. And then I have to check and see whether the summation of these coefficients are 0, C1 plus C2 plus C3. 1 minus 0, 1, 0, which is 0. See, constraint is satisfied. Constraint satisfied. So that means that whatever you have on the top, see, equivalently, you can say H naught. I'm going to say 0 versus HA not equal 0. This is what I'm trying to say. This part, see. Equivalently, I'm going to say, instead of this one, I'm going to say the same one equivalently. My size, see, contrast equals 0 versus contrast not equal 0. Contrast is in such a way that its coefficient, summation of coefficient equals 0. That satisfies the constraint. So if in a situation like this, you are using the t squared like this, okay? These are vectors. Okay? Then you use the pool sample variance, covariance variance matrix. Okay, this one, and if you're going to convert this one to this one, there are degrees of freedom. See? Like that. In a similar fashion, we can use the F test for other contrast as well. What are the other contrast? We saw other contrast on the other page. See? This contrast. See? This contrast and this contrast. This one, I just discuss about this one as well as this one. What we really need is not the theoretical aspect. We need how could you gonna write that one on your on SAS. I just call that one medical, and the class called the pair, The model is, you're going to put that variables equals to pair. The contrast between 1 and 2, I call the 1, 1, 1, 1, uninsured 1, uninsured, and this one Calicare, this one sorry, Medical, the other one is Medicare, this one Medicare, and this one is a private insurance. So you're going to write the same like this. You give that who will be taken into account, 1 minus 1, 0, 0, then mu1 minus mu2, this one mu minus mu3, mu1 minus mu4. See? Then look at the number 7. The number 7. When you do a multinomial, I didn't go to that one, but tomorrow we're going to do that one in detail for time being, okay? Multinomial logistic regression, each group is compared to a reference group. How is then different from an ordinal logistic regression? Why is a ordinal? Multinomial means for y, you have more than 2 options. I'm talking about y variable, okay? I'm talking about y variable, see? More than 2 options. In multinomial logistic regression, there are several groups or layers or options or strata for the categorical response variable. Several. If it is a binomial logistic regression, binomial, see, binomial logistic regression, you have 2 options for y. I'm talking about for the y variable. X variable can be either categorical or quantitative. It's a combo. It doesn't matter. We don't have to worry about that one. We can tackle it. It's not a big deal. And even with this one, if you have a nominal values, like let's say that nominal values for this one, let's say that some income level or the body mass, the something, okay, that stress something like 3 more than, it doesn't matter, several layers, but they were just the labels. Okay, just the labels. Then we can say this one may be multinomial, but it's a multinomial logistic regression, but nominal. If it is ordinal, your variable, which can be that ordered from ascending and descending order, that the options like a grades, A, B, C, D, shoe sizes, see, you can arrange them. The customer satisfaction, like that. See, ordinal logistic regression. In an ordinal one, you don't have to tell that one, but in nominal one, you have to give the reference. The way that in most cases, we put the reference here. See, the diabetes, I'm going to keep the reference 0, 1 means as a my reference. See, diabetes. Looking for diabetes. Here, see. This one, no will be taken with respect to no. What's going to happen? Yes, disease one, I'm looking for the worst scenario, see? And the gender reference 0, then in gender 0, see, male with respect to male, see, male one, see, like that. Exercise, see? Exercise reference 0, 0 means no. Yeah, see. 2 means like here, no, see, earlier they call the 2 here, because they have like more options, 0, 1, 2, 3, like that. We're gonna recode it like that, something like that, okay? So, because of it's already been over there, that we can order that one, okay? But we're gonna talk about that in detail again tomorrow, more detail. Let's go to number 8. Number 8, that we were working on this one right now, but doesn't matter. We're working on this one. Try to answer this one and then try to cover some material, and we can, at the same time that I get we can jump and have a look at the homework a little bit, and then I can upload some notes and then some guidance for the homework and final exam. Okay. So look at that. The following results are from a multinomial. Multinomial means It says where that that already clearly mentioned here. Here, see, response has a response which is marital status. I think merit is a marital status of that one. 1321. So 321. See, more than two options. That's a multinomial. See, logistic because it's a categorical. Logistic because categorical. Multinomial because it has this one. And on the other hand, here we have several. Look at the variable. How many variables for x? X variable. How do you figure out? Education, income, age, effect, mental, health. All are not even being displayed over here. See, all x variables are not displayed over here. Since we have a several x variable, the better way to say this one, multinomial multiple logistic regression. Multinomial multiple logistic regression. We don't call this an ordinal because the marital status you cannot order. See, you cannot order because of that reason. State the overall null hypothesis being tested. State whether you would accept or reject it. Interpret the parameter estimate and odds ratio shown. Yes, the analysis produced other, but in the interest of time, those were not included. Don't worry about those. Okay. So state the overall null hypothesis related to this one based on what you have seen over here. See, you have this one, logic model, marital status being one as the reference category. See, one being reference. See? So they have given this one, AIC, Akaike information criteria, Schwartz criteria, see, -2 log value. And for the global one, likelihood ratio, score, and WALD. And this one effects, see, individual effects. And the odds ratio estimate. That's all. Okay, let's have a look at it. This one. That's the okay. For here. Let me see that. See, this one has the see one whatever the one being given in that that one. I for my convenience I call that one unmarried. Okay. So look at this is the kind of a see, number 8 global likelihood ratio or score or what statistical based test, the global one. What that means, we were talking about the 3 types of that test here. In out of those 3 tests, it's going to be the second test we talk about yesterday, but we're going to talk about that in detail again. Is this current model better than the intercept model? Intercept model. Intercept model. That means this is my model. See, merit. Why? Why has 3 options? That's why mark. This one is categorical. Because of categorical, we are using logistic. It has more than 2 options. That's why we call that multinomial. It has a more regressive variable, more than 1 regressive variable. That's why we call that a multiple. So this one is multinomial, multiple logistic regression. Every word has been utilized for a certain reason. So I call that an unmarried, married, and divorce 1, 2, 3. So here data node, data 1 education, whatever we see over here, then plus income, see the age, mental health, and I put this one some 20th one. Why we have a 20th one? How come I know the 20? How could I know the 20 variables being discussed over here? That's the clue we have here to see. That's the clue. Let's see, would that be the story when we're gonna do all the calculation? We're gonna end up with this one. But when I was doing the calculation later on, I realized, okay, by looking at the degrees in order to keep the consistency, there should be that many variables, regressors. So I set up like that. I'm gonna call that one with the aid of x1, x2, x3, x4, all the way up to x20, blah, blah, blah. That's called the full model. Or you can write this way. See, okay, write this way. I goes from 1 to 20, bi xi, b not separate, or I can put the x naught as a 1. Some people, they prefer to write like that way too. They don't want to keep like this, and they put x naught over here to keep the consistency. Beta naught x naught, given that x naught equals 1. That's a nice way of writing that equations. You can write this way, expanded way, contracted way with the aid of the sigma notation. You see, whole thing being contracted, or that you're gonna separate the beta naught and write this one. Or you can simply write one shot with the matrices. See? That's it, one line. Y equals this one, beta vector prime x vector. See? Look at this, it's transpose. This is the beta. Beta has beta naught, beta 1, all the way up to beta, I'm sorry, beta 20. Should be beta 20. Beta 20. Beta 20, 20 by 1. The other one is x20, 20 by 1 plus beta 20 x20 plus dot plus beta 20 x20. See, you want to write like this way. See, this is 1 and this one. See, this stays as it is. This one will be transposed. That becomes the column vector, becomes row vector, one shot. See, you don't have to write too much. You know, write this one. See, the SI matrix is very powerful. So all the computer being fed with the matrix format, not easy. They can tackle everything. And plus, remember, when you write the equation, since you have 3 options for y, there are 2 equations will be produced. 2 equations. As I wrote that one. This is the proper equation. You know that, not y equals this side. You know, the log of that odds. This is the odds. When you talk about the odds, you can talk with respect to what and whom, who's the odds you're talking about. So I'm going to say log of that one. You cannot simply say y equals that one. I started for my convenience to build up the discussion only. See, like this. No, this is not the right equation. No, you cannot put y here. Okay, I just simply put, but now I'm writing the right one, perfect one. See, log probability of y. Y means the marital status being married with respect to what? That probability being, see, compared with the unmarried one. Unmarried one is the reference. See? That is the one that will be equivalent to this equation on the other side, not y. Why we cannot set that equal to the other side in a least square regression. We had that broader discussion for a reason why we go in this direction, why we use in this format. This categorical, even with the categorical, we have a serious issue because that most of the time least square all the estimates gonna very nicely work at the center of the data. But when we come to the corners, because our data are not gonna go, it's supposed to be between 0 and 1 because of the probabilities, but unfortunately they go outside. Because of that, we remedy that one by revising our equation like this. That's how we got the logistic. And on the other hand, we have 2 of them. Okay, you will see when you display it, you will see 2 of them. See, this one, see, married versus unmarried, and divorced versus unmarried. See, as I put, these should be star, B20 star, B20 star as well. See? Same variable, but you have these ones, betas with this one. See, then your reduced model would be what? Since you have set, can you remember in the beginning what we did was I set up, I'm sorry, not 5, okay, should be all the way to 20 equals 0 at least. It goes from 20. This one, okay, I'm sorry, this one, see, equals 0. beta 1, beta 2, beta 3, beta 4, beta up to 20, and at least one beta I goes from I is from 1 to 20. It goes from 1 to 20. See? Not at least one of them not going to be 0. See? 20. If you put this one, all these zeros, what is left over? What is the reduced model? Reduced model is nothing but this one. See? Just that. Then how could you gonna find that? That's how that this value should be. I mean, like that's the two models. And once you have a two models, this is how you're gonna get your statistics. Likelihood ratio, which is lambda, likelihood ratio. See, it is actually like this: -2 ln likelihood beta. It's a function of beta under h naught divided by L under HA. Since these are log rule, under log rule, I just see the log of deviation quotient is same as the difference between two logs. See, two logs. See? This one. So this one minus something. Not try to get minus 2 times ln minus 2 times L outside. You have a full model, current model. This is the reduced model part minus current model minus 2 ln. They were even being given in a different way. It's called the deviance. See, this part is the deviance. Deviance when beta naught only in that particular the model, minus deviance when all the data is going to be in that one. See, deviance. That's another way you have to look at it. Deviance minus deviance, or deviance of that thing who's being tested. See, these are the tested one. See, beta 1, beta 2, beta 3, beta 4, beta 5, all the way up to beta 20 being tested. Given that, this line means given. See, given that you have a beta naught in that reduced model. See, that's the same thing. It's nothing but chi-square degrees of freedom of this one minus degrees of this one. And then you know the deviance of this one from that table is this one. See, this one, intercept only 91,3331.430. 331,430. And the deviance of this part of the full model minus 2, see, log likelihood times a minus 2 full model is 76,487. 76,487.334. Okay, those two are already got it. And then this is degrees of freedom. It's nothing but at the end of the day, if you get the degrees of freedom of the full model minus the reduced model, is nothing but the chi-square number of regressors in the full model, which is 20. See, that's why it is very consistent with that one. See, 20. See, 20. I'm here. I'm working on these two. Okay, these two, but I got the degrees of freedom from here. But it's the same thing. I'm gonna get the difference between these two, and then I'll show you something. And then that's my log likelihood. See, that's the lambda. And that's the test variable. That's the test variable. That's the test variable. Value is 14,844.096 with the degrees of freedom. That's the same value you're gonna see. This value 14,844.096 is here. See, whatever you take, the difference between these two is same as this one. same as this one. You got that one. So if you're gonna use this one to make your decision, that's more than enough. Then you're gonna see whether you have that the model, would that be better than the intercept model or not? Your current model is better than intercept model or not? What are you gonna do? See, this one you reject H naught. H naught means they were not zero. That means it's better than your current model is better than this model. This one. Not only that, they have their related ones, SCO and WALT. How you can get these ones? You don't have that. How they were derived, how they got that one. You know, by taking these two difference, how do you got those ones even? See, those ones are, we don't do that one. It's already that included all the formulas within our program, so we don't have to worry about anything. So we got this one. So my question is that how these are from this one, they are related to this one. So it's kind of a little bit, I show you for you only convenience, something like this. You can remember that when the logistic regression discussion, I go back to this a little bit real quick and we can stop. Rest we can do. Independent variable, expanded variable, this variable. Then why we are using this one, we had that broader discussion. So then we got the remedy logistic regression, and each patient or trial, see, you have a diseased person, non-diseased person, thinking about you have only two options in the beginning. For y, I'm talking about y, okay? I'm talking about y, this is y, see? When y equals 1 and y equals 0, not x. Those are, we don't have to worry about that. Then, see, then you know the probability of, see, y equals 1 is probability being diseased, probability being the success, see? That's the same thing. I think we don't need that part. This one, show you, see. Then we got the odds, see, odds of deceased to not deceased. See, we got this one. Then we got the logit. Logit means the log odds, called the logit. See, it's same thing. That's the one equivalent to this logistic equation. See, not y. Probabilities. Then not only probabilities, not only the odds, but the logit. Not the probability, not the odds, but the logit. Not y, not probability, not odds, but logit. Remember, you cannot say y equals this one. No. You cannot say p equals this one. No. You cannot say that odds equals this one. No. You have to make sure you get the logit, which is log of odds. See, this is the same way we can write in this format, as I said earlier. See? I said earlier that this one. This one we can write in three ways. Same way. Log, I'm going to write ln p over q like this way, or p over q like this way, or this way. See, you can write like that way. And on the other hand, we know once you have that equation, see, logit equation, sorry, this equation equal to this one. I'm going to go with this one for my convenience. It's easy. If you rearrange this one, then p would be what? 1 plus e to the power of beta naught, betas times x variable. See, betas times x variable. That's how they were related. Then on the other hand, in order to estimate, see, if you parameter estimate, see, you have to get the parameter estimate, your betas, you have to find something. See, you can write the probability mass function, likelihood function. This is the likelihood function. This is the log likelihood function. That's the one that we were utilizing every time. See, yi means like the first patient. Go to the first patient. Let's say first patient, I equals 1. You go to the first patient and see whether he's diseased or not. If he's diseased, I'm going to put 1. If it is not diseased, I'm going to put 0. And p is the value that already we have. See, can you remember? We can evaluate. We don't evaluate. The computer does everything for us. See, p value. See, p value they calculate. They calculate. Go to this one. Beta naught values we know. See, once you get that one, we can. That's what we are trying to estimate. That one p value we try to estimate. See, with this one, and from this one, log likelihood 1. When you take the first derivative of that one, then you get the score function. See, score function. That's the score function. Then you take the second derivative. That's a Fisher information function. See, and get the expected on that one. And if you invert that one, that's nothing but the variance of this guy. See, estimate of p is nothing but the summation of yi divided by this one. P is given by your given data. See, you have a summation of I. I mean, either 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0. How many times? Let's say 40,000 patient here, 40,000 patients. And their variance. Variance is nothing but the flip of the inverse of this guy. See? Standard deviation means of this one. You take the square root, then you take the estimate of the estimate, which is called the standard error. Okay, so you don't have to do that one. But in logistic regression, it looks like this. Your log likelihood function look like this. Everything changes. You go to the first person, your probability gonna change. Your I gonna change. Non-probability, everything changes. See, because of that, it little bit heavier. Okay? Yeah, this is the one. This is the one in the bottom line. This let's see, log likelihood function look like this. Score function look like this. Information function look like this. That's what I want to tell you. Mainly that. That's how you got that these three. See, the computer has been already fed with all these formulas. So they will calculate this one. We're not going to calculate because they were given already. Okay, we just simply did the difference between these two, which is equivalent to this one. Okay. But they are a little bit off, but the degrees of freedom, this one, and then the rest, the odds ratio and everything. I think that when it comes to that, if I go a little bit further down, real quick on this one. Okay, this one, at in the same thing that I'm trying to find out the goodness of it for that one. Under that one, let's say that this something like this kind of example. In this particular example, diabetes, beta naught, beta 1 gender, beta 2 exercise, and beta 3 age. Look at this one. Yes or no? Beta naught. This one categorical. See, female 1, male 0, categorical. Yes or no? Categorical. Exercise or no? But your age gonna go from 18 to 99. It's not categorical. It's a quantitative. How many number of regresses you have? 3, 1, 2, 3. I think 8 profiles. How the profiles are built up, something like that. If you have a quantitative variable, categorical variable, you saw that the other day I did up to a certain point, that how to build up the profiles with the all are categorical. But here I purposely put like a quantitative variable. Look at how we built up the category, these profiles. A, gender. See, man, see, men 0, men 0. Exercise, no. Age, I'm gonna pick a value. I'm gonna pick a certain value X, and then I pick another value, increment by 1 unit, 1 year. How it's gonna change by 1 year. This is the procedure how we're gonna do when we tackle that quantitative variables. You don't have any number to be put over there. You cannot put 80. You cannot put 90. Now you have to simply say, okay, I'm looking for how they change over 1 year, 1 unit, like a marginal. See, marginal cost, marginal revenue, marginal profit. See, marginal cost would be the cost that gonna incur that for producing one more than already being produced. If you're trying to make another one, It's cost that gonna affect, or that income would call the marginal. Same way here, see, x plus 1. So its probability is nothing but 1 over 1 plus e to the minus beta naught, beta, see, 0, see, 0. If you put this one 0, 0, only beta 3 will be left over. And remember that equation, in this equation, see, I plug in into the equation values. 1 over 1 plus this whole thing. So we get this one, but only odds would be this one. So if you need the odds ratio between what? Between, see, anything. See, you can get the odds ratio, see, between, see, that's what we are doing over here, odds ratio. You built up the odds first. See, all these I built up odds. Odds would be exponential of this value, exponential of this value, exponential of this value, exponential of this value. Now I need the odds ratio. I'm going to get the odds ratio of the deceased person. This one, remember, this is being compared with what? Non-deceased, okay? But that's why I simply put deceased inside that one, deceased to non-deceased, okay? OR. But exercise and age, I'm going to fix. I'm going to keep them fixed. I'm going to fix them. I'm not going to do any changes. I'm going to see whether female to male, see, by people who are in exercise. Later on, we can come and then take them, see. Later on, we can give the values and see whether we're going to end up with the same or not. It should be the same, regardless of exercise being yes or no, or age or not. I'm taking into account a female to male group, female to male group. So I'm going to go to female group of the odds of that one exercise and age, age fix, and female group. Look at here. See, exercise and age fix. Then you have this one. See, now I'm going to put the value. Exercise 0, age x. Exercise 0, age x. This one. Male one. Female one, sorry. Female, exercise 0, but the age is x, which is this one. E to the power beta naught plus beta 2 plus beta naught, beta 1 plus beta 3x. See, divided by that same thing for the male. Same thing for the male is what? 0, 0, and x. See? Exercise 0, age, sorry, x plus 1. X plus, oh no, x, I'm here, okay, sorry, I'm here. For the female, x. So this is the male, female, this is the male. See, e to the power of beta naught, beta 3x, and they get cancelled off. You are left over with what? Beta naught, beta 3x cancel, beta 1. I'm going to do the same thing between what? All the options by changing the option on this one. See, look at. Now I'm going to say x equals 1. See, exercise 0, sorry, exercise still 0, but age I'm going to increase x plus 1. See, age, exercise 0, female 1. Let's go to female 1. See, x plus 1. E to the power of beta naught, beta 1, beta 3, x plus 1. Divided by same thing for the male. You get, again, you get the e to the beta naught, beta 1. If you do that one again, by changing, now I'm going to change exercise 1, age x. You get that one. Exercise 1, age x plus 1. Still the same. So bottom line, you don't have to worry about that constant. That's what I'm telling you. You're going to find the that odds ratio between female to male for the this disease one is nothing but exponentiate of the beta 1. Beta 1 is, what is beta 1? Beta 1 is related to the gender. The gender, see, beta 1 is the coefficient in our formula related to gender. Can you remember? That this one. That one. This one. See, beta 1. Beta 1 related to gender. Gender 1, that when it is 1, which is female, is this exists. So that one you take it. If you need the sum, see, Similarly, you to want to exercises to know exercise, go to the exercise that coefficient, exercise coefficient, and raise that power of e. And you need the age to x plus 1, the age. Okay, exercise to know exercise, x, how that been that increased by 1 unit, e to the beta 3. See? In a similar fashion, you can get that one. And these are the estimators for that one. You're going to plug in this one here, then you can easily get the odds ratio. That's the same odds ratio they're going to show over here. We're going to talk about that. It's not related to this example. See, odds ratio means those. See, between several layers and anything, we can build up this one, and their confidence interval as well. Okay. So the confidence interval, you can remember odds ratio, confidence interval. We have done that one. See, risk ratio and confidence is for a given, let's say from the contingency table, we can build up. This is related to even the contingency table. See, in a different example, okay? See, COVID infection, vaccine and placebo, two groups, see, two groups. And this one is Y variable. This is my Y variable, has two options. Whether he's been deceased or not, see, conflict infection, yes or no. These two groups, A, B, C, D, number of people in each one. So then if this is the case, this might contingency table look like that. See, the confidence interval of odds ratio is nothing but lower bound of odds ratio, upper bound of odds ratio. Upper bound is nothing but, sorry, lower bound is nothing but exponential of ln or hat. See, at minus critical value standard error of ln or hat. Ln or hat standard error, this whole thing is 1 over a plus 1 over b. So that's coming from this table. See? Like that. See? Lower bound would be with the negative, upper bound with the plus. P values, you can find that one too. Okay? But we're going to discuss that one in detail. So do you guys have any questions? If not, I'm going to let you go, and then I'm going to work on this one and then make some notes, and then for the answers for that one. Before that one, I would like to show that one, even the homework 4, I think, based on that. So homework 4, so, as I said last time, so, if you want odds ratio, we can talk about that one, but at least when you look at the simple, this one. So I got the same data that we were KISS data, then I built up this time AK22 is the household total income, say, put into the groups. And I put this one we had earlier, mental health, based on this one. And AB1 is the health condition, see, excellent, very good, good, fair, poor, 5 options. Okay, that means this is nothing but, see, multinomial. This is a multinomial multiple. Multinomial means 5 options. Multiple means several x variables. See, sorry, here. So I'm gonna model that one with the education, sedentary, see, gender, and income, and all categorical x variables are categorical. Education, sedentary, sedentary. See, age. Would that age categorical? Sorry, let's see that one. I don't think age categorical. No, sorry. That age is this one, mental categorical, marital status categorical, married. This one, see here, 3 options here. See, married, other, widow, but I put that one unmarried like that, but without knowing that one, but related to this one, it looks like It's like that, married, others, and never married. Okay, that's okay. It's unmarried. Yeah, married. I think I took right. Married, unmarried, just with the married and then this one. That's okay. So anyhow, see, we can run this one and then we can discuss about the result. The same way, see, there's another one, see. Multiple multinomial, see, multinomial, multiple logistic regression. Regression response variable is several group layers classes with the several independent variables. See, but the same thing. See, it's what is it? Descending. Okay, I think that's the same thing. Look like. Okay, that's okay. Let's focus on this one and then have a look at it, this one a little bit, and then we can finish and then we can eat tomorrow. See, otherwise I have to clean up a little bit. So the same thing, I say that when you say, let's say that for this one, I use the other data set here. So yeah, let's take this one. This is kind of like the same thing. But something is missing. That's what I was wondering. No, not that one. That's okay. That's the same thing. Yeah, I had a different one. Anyhow, it disappeared. But that's okay. See, but okay. Let's go to this one. Based on this one, see, if you run this one a little bit real quick, I'm gonna see. I get rid of all that missing data. Even I remedied that one too. Okay. If you feel like there are missing data to be remedied, there should be. Then why is this? Yeah, very high. Yeah, I want to get rid of one of these in terms class, this one, the age. That would see get the results. But if you get the difference between these two, there should be this one for sure. This we can interpret this all the results. Okay, same thing that we saw there. The other one, this one, AB1. See, AB1 has like a 5 groups. So when that's why I want to have a look at it. See here, look at that. Go over here. Maximum likelihood estimates. How many intercept? 1, 2, 3, 4. See, 2, 3, 4, 5. See. Compared to the first one, 1 and 2, 1 and 3, 1 and 4, 1 and 5. See, can you remember when you have last time I showed you when you have a 3 option, 2 logistic equation, two logistic equation. I showed that one earlier. Show that one real quick one more time. Then we have a 2, 3. I'm sorry, 3 in our that is. I showed you like a 3 logistic equation. Certain points I showed 3. Here, see. Here, see. Can you remember? See, when we have a 3 options for this particular example. I see here. See here. See 1. See 2 versus 1, 3 versus 1. That's a 2 example. So you need the beta node, 2 betas. When you have a 3 option for y. In a similar way here, when you have a 5 options, you need what? Your logit should be written with the, see, 2 over ln, same way like here, see, ln, see, ln or log probability, see, y, see, 2 divided by 1, and this one again 3 divided by 1, and another 2, 3, 4 divided by 1, and 5 divided by 1. That's why you need the 4. That's why it's gonna show 4. See, 4 beta nodes. See. So this is Rousseau law. See all these. See, you can see. See. Education, education, education. See. And this incidentary. And 0 and 1, you have only 2. And income, see, mid and upper, see, based on that one, everything being, see, split like that. We're gonna talk about that one in detail. When you split that one, how could you gonna write, as I said over here? So this one, instead of writing like this, is there any way you can write with a single equation? Yes, we're gonna talk about that one too. With the single equation, I'm going to increase that, get the dummy variable. I'm going to include dummy variable, and instead of writing with the aid of the variable, I'm going to write with the aid of the level. With the aid of the level, okay? I'm going to show that one tomorrow for sure, okay? Yes, okay. I think that we can wind up over here and then continue the same discussion tomorrow. If you guys don't have any questions, I'm going to let you go, and then have a good night and stay safe and be well. And we'll see you tomorrow. Take care. Okay.
Thank you so much.
Thank
See
you
you
very much.
tomorrow.
See you tomorrow. Take care. Thank you. Thank you.
Thanks.
Thank you.
Thank you. Bye. Good night. Take care.